In 1948, the Second World War was over, but for America's railroads, peace brought no relief. Instead, it delivered a crisis unlike anything they had faced before. Factories that had once produced bombers, tanks, and artillery shells now turned their assembly lines toward refrigerators, automobiles, steel beams, farm machinery, and consumer goods for a nation eager to rebuild and consume. The volume of freight moving across the United States exploded almost overnight. Boxcars, tankers, and hoppers flooded rail yards from Chicago to the West Coast, and nowhere was the pressure more intense than on the steel backbone of the American West, Union Pacific. Union Pacific's main line was more than track and ties. It was an artery carrying the economic pulse of the post-war United States. Grain from the Midwest, coal from Wyoming, manufactured goods from the East, and raw materials bound for Pacific ports all converged on a single transcontinental route. Any delay along that line was magnified across thousands of miles. And at the center of this system stood a short but brutal stretch of track that had tormented railroad men for generations. Sherman Hill did not look dramatic on paper. It was marked by a simple figure, a 1.55% westbound grade between Cheyenne and Beaufort, Wyoming. To anyone unfamiliar with railroad physics, the number seemed trivial. But to engineers responsible for dragging 5,000 to 6,000 tons of freight uphill on steel wheels with limited friction, it was a wall. Over 7 miles of exposed granite and high plains, trains clawed their way upward against gravity, wind, and weather that could turn savage without warning. For decades, Sherman Hill had been the single steepest and most demanding stretch on Union Pacific's main line, a place where locomotives were pushed to their limits and beyond. Steam power had conquered the hill, but only through brute force and sacrifice. Giant articulated locomotives like the Big Boy burned staggering amounts of coal and water to haul heavy trains at low speeds. Crews worked exhausting shifts, often in punishing weather, while maintenance shops overflowed with worn bearings, cracked fireboxes, and fatigued components. Helper engines were stationed at Cheyenne to shove trains from behind, adding manpower and complexity to every westbound movement. It worked, but it was inefficient, expensive, and increasingly out of step with the modernizing railroad industry. After the war, the problem intensified. Freight volumes surged by as much as 50% in a single year. Dispatchers watched yards fill faster than trains could clear the grade. Every day, westbound consists waited their turn, engines idling, crews on the clock, schedules slipping. Sherman Hill transformed from a difficult stretch of track into a strategic bottleneck. If Union Pacific could not push more tonnage over that hill, it would lose its competitive edge in a rapidly changing transportation landscape. Diesel-electric locomotives were supposed to be the salvation. Across North America, railroads were abandoning steam in favor of diesels that promised lower labor costs, easier maintenance, and greater reliability. Union Pacific embraced the trend, but on Sherman Hill, the promise fell short. Early diesel units simply lacked the raw power required for sustained heavy grades. A single EMD F3 produced about 100 horsepower. On flat land, that was adequate. On Sherman Hill, it was nearly useless by itself. To move a heavy westbound freight, Union Pacific had to lash 4, 5, sometimes 6 diesel units together. Each unit required fuel, inspection, and maintenance. Each one introduced another set of wheels, another generator, another traction motor that could fail. If one unit lost power or tripped a protective system halfway up the climb, the entire train risked stalling, blocking the line, and compounding delays. The operational burden was immense. Crews referred to the situation as a squeeze. Dispatchers juggled schedules, held trains in sidings, and prayed for uninterrupted runs up the grade. But no amount of planning could change the underlying physics. Diesel power, as it existed in the late 1940s, had not solved Sherman Hill. It had merely replaced one expensive system with another. Inside Union Pacific's boardroom, patience was wearing thin. The financial ledgers told a brutal story. Operating a single Big Boy steam locomotive over Sherman Hill could cost more than $500,000 per year when fuel, water, labor, and maintenance were accounted for. Diesel lash-ups were supposed to reduce those costs, but running multiple units with multiple crews eroded the savings. Worse, delays were hurting the railroad's reputation for reliability at a time when trucking and rival railroads were aggressively competing for freight. By 1948, the conclusion was unavoidable. Incremental improvements were no longer enough. Union Pacific did not need more locomotives. It needed fewer, stronger ones. A single machine that could replace an entire string of diesels. A locomotive that could climb Sherman Hill alone, without helpers, without hesitation. Meeting minutes and internal correspondence from that period reveal a sense of urgency bordering on desperation. Freight was backing up. The post-war boom showed no signs of slowing. As one executive reportedly summarized the problem, the railroad did not need a flotilla of small boats. It needed a battleship on rails. Whatever the cost, Union Pacific would pursue the most powerful locomotive ever built. While railroad executives wrestled with economics and operations, a very different line of thinking was taking shape inside General Electric. Vincent Mertz, an engineer immersed in the emerging world of gas turbines, was watching the aviation industry redefine what engines could do. In the skies over Korea, jet aircraft like the F-86 Sabre and the MiG-15 were demonstrating unprecedented speed, climb, and power. At the heart of these machines was the gas turbine, a radically different approach to generating force. Unlike piston engines, turbines relied on continuous rotation. Air was compressed, mixed with fuel, ignited, and expelled through turbine stages that spun at thousands of revolutions per minute. The result was smooth, relentless power delivered by a mechanism with far fewer moving parts. There were no pistons slamming back and forth, no crankshafts twisting under explosive loads. From a purely mechanical standpoint, turbines were elegant. Most railroad engineers dismissed the idea immediately. Turbines were loud, ran extremely hot, and were notoriously inefficient at low power. They thrived at steady, high output and performed poorly when throttled back. Railroads, with their frequent stops, variable loads, and long idle times, seemed like the worst possible environment for turbine power. Mertz saw something others missed. Sherman Hill demanded exactly what turbines excelled at: sustained, continuous power under heavy load. Trains did not need delicate throttle response on the grade. They needed brute force, delivered relentlessly, mile after mile. In his notes, Mertz captured the appeal succinctly. Aviation power adapted for rails could deliver an order of magnitude more horsepower per pound than any diesel engine. General Electric began experimenting. Early test installations roared to life inside GE facilities, pushing turbine components to their limits. Engineers measured vibration, heat, and material fatigue, developing new alloys capable of surviving extreme temperatures and rotational speeds. Massive generators were designed to convert turbine output into electricity for traction motors, preserving the familiar diesel-electric architecture while replacing the prime mover with something radically different. One of the biggest challenges was environmental. Aircraft turbines operated at altitude, ingesting relatively clean air. A locomotive turbine would face dust, grit, insects, and debris kicked up from the track. Engineers designed heavy-duty intake filtration systems to protect the turbine blades from damage. Every test revealed new problems, but also new solutions. Union Pacific followed these developments closely. Diesel lash-ups were straining under growing freight demands. Steam power was bleeding money. The turbine offered a clean break from both. It was a gamble, but the cost of inaction was higher. The first turbine locomotives entered service in the early 1950s, producing around 100 horsepower. They were experimental and temperamental, but they worked. Over the next few years, power increased to 5,500 and then 7,500 horsepower as engineers refined designs and operating procedures. Each iteration pushed closer to Union Pacific's original mandate. In 1958, that mandate was fulfilled. Union Pacific took delivery of the GTL 8500, the most powerful locomotive ever built. Crews quickly gave it a nickname that captured both awe and intimidation: the Big Blow. The Big Blow did not resemble a conventional locomotive. It looked like a mobile power plant. 3 units stretched nearly 200 feet from nose to tail. At the front was the cab, elevated high above the rails, offering crews a commanding view but little escape from the noise and vibration. Behind it sat the turbine car, a massive steel enclosure housing a gas turbine spinning at nearly 7,000 revolutions per minute. Trailing at the rear was a fuel tender that looked more like a small oil tanker than railroad equipment. The numbers were unprecedented: 8,500 horsepower, more than 5 times the output of a standard diesel unit of the era. The turbine car alone weighed over 200 tons when fueled. The generator inside was so large it had to be craned into place during construction. When the turbine spooled up, the sound was unmistakable. A high-pitched scream closer to a jet engine at takeoff than anything previously heard on rails. Yet power alone did not make the big blow revolutionary. Its true advantage lay in fuel. Instead of burning refined diesel, the turbine ran on bunker C, a thick, tar-like residue left over at the bottom of the oil refining process. In the 1950s, bunker C was practically worthless. Too dirty and viscous for piston engines, it was treated as industrial waste. Refineries were happy to sell it for pennies. Union Pacific saw an opportunity others ignored. The Big Blow's fuel tender was fitted with heating coils that kept the bunker C at approximately 250 degrees Fahrenheit, turning sludge into a pumpable liquid. Once inside the turbine's combustion chamber, the fuel was atomized and ignited in a roaring blue flame. At roughly 3 cents per gallon, bunker C was dramatically cheaper than diesel fuel. The turbine could run hundreds of miles between refueling stops, burning fuel that few others could use. This fuel strategy transformed the economics of brute force. On paper, the Big Blow could replace 5 diesel units, require fewer crews, and operate on fuel that cost a fraction of conventional alternatives. Every mile it ran promised savings. Every train it hauled without helpers reduced labor and congestion. Operating the turbine was unlike anything railroad crews had experienced. Startup was a ritual that felt closer to aviation than railroading. Fuel had to be heated and circulated. Systems were checked and stabilized. The turbine was brought to idle, then carefully spooled up to operating speed. Once at power, the response was immediate and overwhelming. On Sherman Hill, the effect was dramatic. Where steam giants crawled and diesel lash-ups strained, the Big Blow surged. One locomotive, 3 units long, hauled 100 loaded cars up a 1.5% grade at speeds approaching 40 miles per hour. For crews who had spent careers battling the hill, it felt like defying gravity itself. The sound announced its arrival long before it appeared. Windows rattled in Cheyenne, dogs barked, people stepped outside just to watch the monster pass. Engineers compared the noise to multiple jetliners spooling up simultaneously. Inside the cab, vibration was constant. Ear protection became mandatory, and even then, long shifts took a toll. The performance statistics bordered on unbelievable. Although turbine locomotives made up less than 2% of Union Pacific's fleet, they hauled more than 10% of its freight. Each Big Blow averaged over 100,000 miles per year, running almost continuously between Council Bluffs and Ogden. Sherman Hill, once the railroad's greatest bottleneck, had been reduced to a conquered obstacle. The power was so immense that it sometimes overwhelmed the hardware behind it. In one well-documented incident in 1960, a turbine started a heavy train too aggressively on the grade. The coupler on the first car snapped, sending the rest of the consist rolling backward down the hill. It was not an isolated event. Engineers quickly learned that careless throttle use could literally tear steel apart. Operating rules were rewritten to account for forces previously unknown in railroading. For nearly 2 decades, the turbines reigned. They were loud, hot, and intimidating, but they delivered exactly what Union Pacific had demanded. Critics called them monsters. Crews often described them as terrifying and addictive in equal measure. When a Big Blow crested Sherman Hill at speed, without helpers and without delay, it felt like victory over both nature and tradition. Yet beneath the triumph lay a flaw that no amount of engineering could eliminate. Gas turbines hated waiting. Unlike diesel engines, which could idle quietly and sip fuel, turbines consumed nearly the same amount of fuel at idle as they did under load. On a busy railroad, waiting was unavoidable. Red signals, sidings, yard congestion, meets with opposing traffic. Every minute spent standing still translated directly into wasted fuel and rising costs. For a time, cheap bunker C masked the problem. Fuel costs were so low that inefficiency was tolerable, but the global energy landscape did not stand still. In the 1960s, the petrochemical industry expanded rapidly. Advances in refining technology turned heavy oils into valuable feedstocks for plastics and synthetic materials. What had once been waste suddenly became a commodity. The price of bunker C rose sharply. By the late 1960s, it approached the cost of diesel fuel. The economic loophole that had justified the turbine experiment closed abruptly. Internal Union Pacific memos painted a bleak picture. Fuel costs had doubled in less than a decade. When maintenance, downtime, and operational inefficiencies were factored in, turbines cost significantly more per mile than modern diesel consists. Noise added another layer of pressure. As towns expanded along the rail corridor, residents complained of sleepless nights and rattling windows. The turbine scream, once a symbol of industrial power, became a political liability. While no outright bans were imposed, local pressure mounted. Union Pacific found itself increasingly constrained in where and when turbines could operate. In response, the railroad began parking turbines in remote sidings, idling them far from populated areas. Ironically, this made their inefficiency worse. Burning fuel while doing no work, the big blows hemorrhaged money. By the end of the 1960s, the verdict was unavoidable. In 1970, Union Pacific withdrew the turbine locomotives from regular service. They sat silent in deadlines, enormous machines built for continuous motion, now immobilized by economics and circumstance. Most were scrapped by 1979, their engines dismantled before the oil crisis of 1973 could even reshape global energy priorities. The big blow did not fail because it lacked power or reliability. It failed because the world around it changed. Fuel economics shifted, society demanded quieter machines, diesel technology advanced rapidly, producing locomotives that were more efficient, more flexible, and powerful enough to meet freight demands without the turbine's drawbacks. Today, railroads chase efficiency, emissions reductions, and silence. Yet the need for raw, disruptive power never truly disappears. As freight volumes grow and energy systems evolve, the question lingers. Will there come a time when railroads once again embrace machines that challenge limits even if they offend polite expectations? Progress is not always quiet. Sometimes it screams, sometimes it shakes the ground, and sometimes, like the big blow, it burns with unmatched intensity for a brief moment before vanishing into history, leaving behind a lesson written in steel, fire, and noise.